All right, you guys, another tinkering update since I've done a lot of, filming in my car, 3 in a row. It's been a long week, but getting closer. So my plastic plexiglass protractor here, I epoxied the magnet in place. It's a little bit off, as you can tell by this side is a little bit bowed out. So I might re-drill one of the sides so that this screw nut bolt washer setup can flatten that out, but then it's going to be a little bit loose. So I feel like this should be able to make it through the coil, and it's circular enough that it's not going to hit the edges of the coil. That's the main concern, especially not hitting the magnet, because then it's going to knock it off. But okay, last update that I did at the very end, none of you probably watched it, but that's all good. Or for the few of you that did, I was trying to use the Hall sensor that I got to estimate the magnetic field strength of the magnet on here, because having an accurate readout of the magnetic field when the magnet is swinging through the coil is pretty critical for validating Faraday's law of induction. Because even though I could get the waveform and the timing and an approximate value of the field strength, if I don't have that actual d phi sub b dt, from also having the measurement of the angular velocity of oscillation that I'm driving on this protractor attachment, if I don't have that, then I can't actually validate my measurement of induced EMF, coil winds, coil dimensions, magnetic field strength, have it all put together. So I really need the magnitude of the magnetic field strength. So I was like, okay, I'm going to use this Hall sensor. And I'd previously been using it with a weak, just tiny little button magnet, that you could put stuff up on a fridge with in order to do my coil winding jig. So that is a substantially weaker magnetic field, and all I needed was just kind of have an off-on reading for when the drill chuck would spin around as the magnet would pass by the Hall sensor, being able to see a big enough differential that then I could use that to count the number of coil winds. So, but this is a 1/2 inch diameter, 1/2 inch height cylindrical neodymium magnet, and it's important that this is neodymium, a stronger one, so that I can get, I guess in principle, a stronger induced current. And my thinking for that is that I could then have a voltage divider to step down the current to be in the range of my analog to digital converter if need be. Or I suppose I can make another coil with fewer winds, but I can change my coil dimensions in that way by making different coils, perhaps if need be, voltage divider if need be. But then you can't really change the physical characteristics of your magnet. You can get different magnets, but I was just like, okay, I'm going to commit to this because of like the size, and I went with the strong one, neodymium. As a result, I was like using this to here. I've even got my Hall sensor on top of Maxwell's Treatise on Electricity and Magnetism Volume 1 hooked up to my Raspberry Pi, and I figured out why it wasn't working from the video before. Basically what it is, I might as well just document it now, is that I had the magnetic angle encoder from the back of the stepper motor. This is the 3D printed part that fits on. I had this on the motor plugged into the Raspberry Pi, magnetic angle encoder plugged into the Raspberry Pi, and then I had the Hall sensor on the ADC also connected to the Pi. And this magnetic angle encoder uses the I2C interface. I forgot what I2C stands for, but it's a digital interface. And so I also had the analog to digital converter on the I2C interface. And the thing about the digital interface, the I2C digital interface that is that you can have multiple inputs onto the same GPIO pins on the Raspberry Pi. So that way my GPIO header doesn't get crowded up. And there's only like one I2C input. There's like an SDA pin and an SCL pin. And you can have multiple inputs going into those two pins as long as they have different digital addresses. So when it wasn't working before, the problem is I wasn't grounding the address pins on the ADC. So I thought that you could just float them and it would have the default I2C address of 68, but I needed to ground those address pins instead of having them floating in order to get the address to be 68. Anyways, so in principle now I can have the magnetic angle encoder on the back of the stepper motor, and although I mentioned in previous video the accuracy of this, I still need to work out because it is not exactly reading out a correct angle. I can basically only get a correct return to an original starting point. Maybe it's this attachment, maybe it's something else. I don't know. I still have to troubleshoot that. But I can have the magnetic angle encoder and the ADC output on different addresses, but going into the same two I2C pins on the GPIO header on the Raspberry Pi. And since there are 4 channels on the ADC, then I can eventually put that Hall sensor inside the coil. So the Hall sensor's on the ADC, and then have the output induced EMF from the coil onto another channel on the ADC. That way I've got the coil induced EMF, the magnetic field strength readout on a Hall sensor. Both of those are on the ADC. And then the ADC is going to I2C on an address, and then at a different address I have the magnetic angle encoder also on I2C. All of those are going to the same I2C pins on the Raspberry Pi. So the Raspberry Pi then in software, I've got it all at once. At the same time, the Raspberry Pi can be controlling the stepper motor on that Adafruit driver, which my only qualm about that, well, 2 things. One is that I haven't been able to change the speed very easily on the stepper motor, or I haven't tried yet. And going back and forth is a problem. So the goal obviously is I want this to oscillate, the plexiglass protractor to swing back and forth. As you can see, I used to have some collars epoxied on here, and the epoxy will just kind of like break off from the oscillation because it'll like swing to one point and then it has to like have force to go in the opposite direction. And you can't really see, but it's like this is kind of, there's like a little bit of weight to this, especially with these bolts on the ends. So I might try to like find some smaller ones or something like that. Anyways, but the epoxy will break off. But if I had this directly on the stepper motor, in order to change directions, then you're basically like alternating the sign of the applied voltage on the coils inside the stepper motor. So when you switch directions, there's like that residual EM energy, and so the changing of directions of the stepper motor isn't very consistent. Sometimes there'll be a little bit of a delay. It might throw off where basically like the starting angle is of the motor output. So I mentioned in a previous video the design problem trash throwaway vlog that I need to 3D print a Scotch yoke. That way the motor is constantly outputting at a single direction. Clockwise or counterclockwise, it's going to be clockwise, but it's always going to go clockwise, and then the Scotch yoke will provide the output to this, which will then oscillate. And maybe I'll put up the image on screen of like the principle, the idea of the mechanism. I had drawn out another one, but I was like, okay, this is a little bit too much. I'm basically using the concept from like a metronome, and that by tuning the radius on the stepper motor where my output crank is, then that'll change the angle width of output on the Scotch yoke. And from my preliminary tests, it's like probably only going to be like 45 to 60 degrees either way out. If like centered is, this is like 0 if we're at like 90 degrees on the protractor. This is 0 and going 45 degrees to 60 degrees in either direction. That's probably going to be enough. And yeah, but okay, so like a month ago, I renewed my membership at the makerspace where I can use a 3D printer, and I only have like less than a week. I have like 6 days. I'm not going to print it today, so it's going to be like 5 days to actually like get it done. But I have literally literally every single other part. Like I have it sketched out. I have the other mount that I'm gonna put on like a little box enclosure. So there's like a mount above, and there's gonna be this threaded ball bearing shaft with an output rod, and then, you know, the output is coming off of here, goes down, motors here. So like motors down here, the threaded ball bearing shaft with the output axle is up here, okay? And then I'd have a box enclosure around this, and there'll be kind of like a wheel here, and that's where there's the crank that's going to be attached here. The crank, the output is like up here on this, okay? Spinning this. This rod right here, this dowel pin, is too thick for my plastic protractor. So I ordered a coupler to get down to this, which is just slightly bigger than the D shaft on the stepper motor. But then it's kind of like, you know, luck of the draw of buying all these parts on Amazon is that these dowel pin rods were not the size that they said that they were. Like this, I bought the rod, it said it was a 5mm shaft. It's more like 7mm. And the bore of this threaded flange mount, whatever you want to call it, the bore diameter is like 8mm is the rating. So the diameter of the bore is 8mm, and when the part got here, that's correct. But then I put a 7mm dowel pin through it. The 7mm dowel pin was claimed to be 5mm. And then the coupler that I originally got, it was like the 8mm end is smaller than this, and it was supposed to go from 8mm to 5mm, and the 5mm input was too small. So yeah, it's just kind of like luck of the draw, and you know, it's no big deal because I can return it on Amazon and all that, but it just kind of is like a loss of time, you know, having to like randomly order stuff and then test it out, and then it doesn't work, and then have to go and return it. But I'm very thankful that I'm able to do that in the first place. So yeah, I'm getting a lot closer. Oh, and the other thing though is, so the magnetic field strength of this magnet, let me back up. If you know how Hall sensors work, the principle is that it's basically Faraday's law of induction. It's probably not exactly that, but it's basically like, okay, you move this magnet near the Hall sensor, and there's a quiescent voltage in the sensor. You bring the magnet closer, raises or lowers that voltage, depending on if you're on like north or south pole magnet. And this magnet is so strong that it exceeds the range of this sensor. So I thought, okay, well, maybe I'll just like use a voltage divider to bring it down. Well, that's not enough. And also, by the strength of this magnet and the sensitivity of the sensor, I'm basically like in the saturation range of the sensor anyways. So even if I do use a voltage divider of just like 2 resistors, then even when this thing is like swinging through, it's like basically always going to be in the saturation range of the particular Hall sensor that I have. So I got a different one of those. I also got an op amp, so that the Hall sensor that I got, that I just ordered, has a higher magnetic sensitivity range. And it's also important because like it needs at that higher range like a good window of linearity, you know, like once you hit that saturation, you're not really linear anymore. So it has a higher sensing range, and by being at that higher range, there's like more linearity that I have to work with. And then ordered an op amp so that I can open that up, like zoom in principle, and like, you know, capture the range of the magnetic field at that higher sensing range and get a better readout of the magnetic field strength. So got another Hall sensor on the way, op amp on the way, glued my protractor together. I didn't, you know, shave the part where the magnet sits very well. Otherwise, you know, that's what led to this little gap to be here, but we can live with that. And then I have to 3D print a Scotch yoke. Most likely I'm gonna have to like sign up for another month of the membership at the makerspace, but that's like $30, so that's not a big deal. And I hope you guys like the suit that I'm wearing. Today it was announced that Robert S. Mueller III died, and that's not why I'm wearing this suit, but I'm gonna wear a suit in his honor tomorrow, specifically the blue pinstripe suit with the white Oxford button-down collar shirt with the foulard tie, and his specific brand of Casio watch, because Robert S. Mueller III, rest in peace, was a fashion icon, and he inspired me back in 2017, 2018 to even seek out blue pinstripe suit, the button-down collar, foulard ties, and I was already suited up today on Saturday. It's a little bit after 5. And he inspired me in the first place to have that old Ivy League style. So it's truly an end of an era in terms of menswear and fashion, because he lived out the Ivy League style, and he defined in his old age what Ivy League style even means, you know. So tomorrow I'm gonna wear the Robert S. Mueller tribute suit, and I hope the epoxy doesn't snap off or crack my piece here, but I could probably even just like tape this down right here, because it's like a gap, and I can just like tape it down, then there isn't that gap, because I was holding it together with like vice clamps, so that's probably better than drilling another hole. But man, the bolt washer nut setup does add weight to this, and that makes the stepper motor have to do more work in order to swing it. So, but anyways, it's been 20 minutes. I will see you guys in the next one.